Welcome to the latest video in our series on diffusion image filtering. In the last video we finally studied the two-dimensional heat equation, and then we saw how to implement a blur filter using it in a real image. Well, last video was a very theoretical video. We mostly set up the vector formalism for the Fourier transform. And the idea is that this one will be like more of a practical one. We will discuss the issues that arise when we try to implement a practical numerical method for the 2D heat equation. In any case, what we saw in the previous video is that if we had an image which was a collection of points, right? In complete analogy with the 1D case, we would take the FFT of this. The FFT had an analogous formula for 2 dimensions, and then we would have again a rectangular array, but now in frequency space, right? And we saw that, well, these, if we say here that we have like this is frequency 0, this is the nx and y, what these things actually meant was that here at the middle we had the Nyquist mode, which was the largest one, then they stayed negative. So if we filled this array with a Gaussian here, more or less this, right? And then we multiplied this thing with the original image, and then we took the inverse Fourier transform, then we would obtain the image blurred, which was the solution to the heat equation at 2D, and then the effect of this would be a blur, right? This is what the heat equation does to an image. Alright, and then this approach is like very fast, very useful, but the problem is that it has no generalization if we add non-linear terms to the heat equation later, right? Because the Fourier transform only works well if your equation is linear, and sometimes we need non-linear things to get to use a more general filter. So, and then what we saw in the 1D case is that instead of using the first Fourier transform, we would use something like the Crank-Nicolson method or any numerical approximation in general to solve this. And then we'll see whereas the analogy goes of the Crank-Nicolson method for the 2D case, which is the ADI, which is we're going to study now. Okay, so without further ado, let's start. Then what is the ADI? Is the alternating direction implicit method. So let's going to start implicit methods for the 2D equation. So here we're going to introduce some formalism, just like we introduced some notation for the discretized values at the field. The 1D equation we're going to introduce to the 2D. We call Uij super n is u at the I delta r position, j delta r position, n delta t, and then we have that the Laplacian, it is the sum of the two second derivatives, and then we do this with the central difference approximation. We approximate this by ui minus 1j minus 2 uij plus ui plus 1j divided by delta r squared plus uij minus 1 minus 2uij plus uij plus 1 divided by delta r square, right? And if we gobble up everything, we have ui minus 1j plus uij minus 1 minus 4uij plus ui plus 1j plus uij plus 1 delta r square. So graphically what this means is, if we go back to our sketch, we are approximating the Laplacian of a given point depends only on these neighbors, right? And these, this, and this. So, and of course these here, right? So we approximate the Laplacian by this guy and its neighbors, and as in the 1D case, this, if you do this with an explicit method, it should only be valid for a very small times, or else the method would be unstable, right? So if we put again the 2D heat equation, we can just do like an Euler method, for example, approximate this, the time derivative of an Euler method, and then put an explicit one. But then we would have the same problem as in the 1D case, that for a very large time step this scheme would be unstable, and we could fix this with an implicit method like the backwards Euler or the Crank-Nicolson. But now another issue arises, right? Because we have this now, remember that the implicit method in the 1D case, when we wrote the matrix equation, this matrix equation was tridiagonal, right? It was something like this, right? It is what we wrote in the previous videos. We had something like this, and so on. But now if you, like, for example, use this, I think this is called normal ordering, that what would be the matrix equation for an implicit method in this case, with this notation it would be, so if in the case of the Lena picture that has like 512 pixels by 512 pixels, so we would have around 500 times 500 variables, and then a matrix equation, the dimension would be 250,000 by 250,000, and it would not be tridiagonal. It would have a band, you see here, it would only be tridiagonal if we had UK plus 1 and UK minus 1. But because of this dependency on several dimensions, it actually had UK minus width, UK minus width. So in our case, there would be like other terms here, right? With this distance, the width, which in the case of the Lena picture would be like 500. So it would not be a tridiagonal system, it would be a banded system. It would still be a sparse matrix, but the band would be 500, and this would be like much harder to solve than in the 1D case. So when we actually implement implicit methods for the 2D, we have this problem that, unlike in the 1D case, we do not arrive at a tridiagonal matrix, right? So the ADI method, it's like this to solve exactly this problem, right? So what is the ADI method? So the idea is to split the Laplacian into two operators, which is the LX, which is the central second difference operator in the x direction, or it's essentially like the central difference in the x direction. We are not divided by the delta r square thing to get the second derivative here. And then in Ly, we do the same in the y direction. So here you have I minus 1, I plus 1, and here we have j minus 1 and j plus 1, right? And if we use this notation, the 2D equation for the Crank-Nicolson method would be uij at the n plus 1 time minus uijn divided by delta t equals d divided by 2 delta r squared lx plus ly uijn plus 1 plus uijn. This is the pure Crank-Nicolson method, right? Cool. But the idea of the ADI is, instead of going to this time step delta t directly, we do it in two halves. And in the first half, when we go to n plus half, we evaluate one of the coordinates explicitly and the other implicitly. So here, for example, we are going from un to un plus half, but we are evaluating the central difference of y at the time step un, but the difference of Lx at the time step n plus half, right? And when we go to n plus half to n plus 1, these roles are reversed. Now we are evaluating the central difference of x at n plus half and the central difference of n plus 1 at y. So what this means is that we evaluate the one of the coordinates explicitly in one half time step and the other coordinate implicitly, and in the other half time step these roles are reversed, right? This is the idea of the ADI, and the whole point behind this is that in each half step we have several independent matrix equations, each of which is tridiagonal. So instead of, for example, having, in the case of the Lena picture, instead of having a matrix of size 250,000 square, the ADI would reduce this to around 500 squared, of course, like 500 matrices of this time, and each of these would be tridiagonal, and then this is much easier to solve, right? And then there's, of course, that pressing question, if you should be familiar with this stuff from the other videos on approximation methods that we did. What is the stability analysis of this method? Now, if you remember the stability analysis, we substituted the ansatz for our scheme, right? And here we also have an ansatz, but it's a bit more complicated. We say that we have an exponent for integer time steps, an exponent a for integer time steps, and an exponent b for half integer time steps. And the idea is that if you have a frequency mode, it will grow at a rate in this x half step and another in this y half step. And this is the reason that we have like these two different exponents. Well, as in the 1D case, we introduce this alpha operator, and then when we apply the operators, we'll see that 2 1 minus cosine term that we have met several times already. And if we substitute this like in the equations, we see for the first one we'll have bkl to the power of n minus akl to the power of n equals minus alpha bkl to the power of n 1 minus cosine k delta r plus akl to the power of n 1 minus cosine l delta r, and the second equation akln plus 1 minus bkln equals minus alpha bkl to the power of n 1 minus cosine k delta r plus akln plus 1 minus cosine l delta r. And to solve this, we will isolate b KL to the power of n in this size, and AKL in the other side, and then in the first one we'll find BKL to the power of n 1 plus alpha 1 minus cosine k delta r equals AKL to the power of n 1 minus alpha 1 minus cosine L delta r. And in the second one will be BKL to the power of n 1 minus alpha times 1 minus cosine k delta r equals AKL n plus 1 plus alpha 1 minus cosine L delta r. And if we divide the second by the first, we have the value of AKL, which is the only one that matters for us because we'll always run 2 time steps, right? And we have that AKL is 1 minus alpha 1 minus cosine k delta r, 1 minus alpha 1 minus cosine L delta r, and the same thing in the denominator if we change the sign of alpha from minus to plus, right? And well, first question, is this thing stable? And yes, because if you remember from the Crank-Nicolson method, we had something very similar. We had like 1 minus alpha 1 minus cosine k delta x divided by 1 plus alpha 1 minus cosine k delta x. So the frequency response of the ADI is, well, is the product of Crank-Nicolson responses, one for the x frequency and another for the y frequency. And if you remember the analysis that we did, was that this term here, these two factors here on the left, they are always between minus 1 and 1, right? So, and then if we multiply two things that are between minus 1 and 1, we get something that is between minus 1 and 1, so that the product is also stable, right? And if we write the exact FFT response, we have that it is this, it's minus alpha k delta r square plus L delta r square. And for a property of the exponential, we see that it is also the product of something from the x frequency times something from the y frequency, alright? And if you remember, what was the reason that we chose the Crank-Nicolson method in the first place was because if you expand this term here in the left and compare with the exponential, for a large alpha, they are fourth order in the frequency, right? And then here we have the same thing, because since each of these terms here are accurate up to fourth order, then the whole thing is accurate up to fourth order. So we see that the ADI has all the nice property that the Crank-Nicolson method has. It is unconditionally stable, and it is accurate to fourth order for large values of alpha, which is pretty good, right? Now, more or less some implementation details. Well, this is actually very simple, just picking these equations here and then moving stuff around so that we have the implicit guys on the left and the explicit ones on the right. And you see that this in the right side we do a convolution, and in the left side is the matrix equation that we need to solve. It's a three-diagonal matrix equation. Here it is in I, is in J. So our loop is more or less, so we do a convolution, we transpose the matrix, well, because usually the way that matrices are saved in programming languages, it's only the array, the row is contiguous but not the column, so the programming languages lets you access the row vector pretty easily. So what we usually do is we do a convolution, we transpose, then we solve the linear system, then we do a convolution again, then we transpose, and then we solve the linear system, and so on, right? And this is more or less how it's done in practice. It's pretty elegant, and these implicit matrices, you need to compute them only once. They're kind of like time independent, right? and you can just need to solve the linear system for them. Alright, so now, and then another very interesting point which I mentioned when we solved in the FFT was the topic of boundary conditions, right? So because if you remember what we have been doing in 1D case up to now is that we've been using Dirichlet boundary conditions, where we require that in the 1D problem we have always used Dirichlet boundary conditions, where these guys here, they need to be 0, right? But when we work in the 2D case, it's really more convenient to use Neumann boundary conditions, where we require instead that the derivative at these points is 0. So we would have something like this, right? We want the derivative to be 0, because this will conserve the total amount of field. And then you should be asking yourself, how do we do this? Well, if you see from the FFT case, what we did to achieve this, we completed the signal with, pretend that this is symmetric, right? We completed the signal with an even function, right? And then we assumed that periodic boundary conditions, that this guy is equal to this one. This is what we do with FFT. Well, if we use this condition, you can see that when we sample, if we do something like this, so we are sampling, we have this guy, and then this guy, and then this one. You can see, so when we're going to evaluate the next point, this guy should look to the guy on the left and the guy on the right. But if the function is even, then this guy on the left is just the guy on the right, right? They're the same thing. So if you can imagine that if this guy does not exist, so the dependency on this guy is multiplied by 2 to compensate. And that is just how we do implement Neumann boundary conditions on this method. When we do the convolution and then we are at the boundary point, instead we have to look at 2, we only look at 1, but with double the value. And the same for this other guy here, the same arguments apply. And that's all that we need to do, really. Right? So without further ado, let's go to the code. So just to explain more or less how this is working, I will not run here because the way I implemented in NumPy, it is kind of slow. It takes around 3 minutes to run, but for our purposes it won't matter much, because in this course we are targeting a C++ implementation. We're only using the NumPy one as an example, but I'm pretty sure that like a NumPy or a SciPy specialist could optimize what I'm doing here, because I think the slow thing is because I am like extracting vectors of the matrices all of the time, and then this causes some calls to Python. I'm pretty sure a SciPy expert could like put everything in one very large matrix and solve everything pretty fast. But like I said, I would not bother this here. I just want to show the idea, and I don't care if it's slow at this point, right? So the first thing that we do, we have this function here to set up the implicit matrix. We did, and then as before we have a main diagonal, which is this guy here in the nodes, right? This 1 plus alpha with the main diagonal, and then the lateral diagonal of minus half alpha here, which is this, alright? And this times equals 2 here is the Neumann boundary conditions I told you about, right? If we are doubling at the extremes, we are doubling the influence of the neighboring point. And then this is just the scipy command to construct the matrix. And then now our convolution, if you remember before, our convolution was with 0, the border. But now for Neumann boundary conditions, we are just like we are adding these y1 and y minus 2 terms here to implement this in the convolution, right? To set up Neumann boundary conditions. And then the rest, well, just this is kind of copy pasted from the code of the previous video. We're just loading up the image and evaluating the image with the FFT so that we can compare our result. Here we chose a blur of 10 around, well, 10, there is like a factor of 4 there for the dimensionality, but it would be like 10 or 40 pixels or whatever, depending on your definition of the width of the Gaussian. And then, well, this here just computes the FFT, and then this guy here is the code for our ADI method, right? We divide it to 10 time steps, and then we have the alpha is the blur we want to apply divided by m, and then we create a NumPy array out of the image. We extract rows and columns, and then we create a matrix for the rows and a matrix for the columns. Well, in the case of the Lena image, because it's a square image, it will be, this matrix will end up being the same in every direction, but as I mentioned, this is not true in general for rectangular ones. And then we run this loop here m times. So what we do for every row, we replace that row with the Neumann convolution of itself with alpha. Then we transpose the matrix, and then we solve a linear system. Then we do the convolution again. We transpose the matrix, and then we solve the linear system. And we do this m times, right? Like I said, this, I don't think that's the most optimal way to do this in NumPy, because this needs to extract vectors like all of the time, but it works, and you can see that the result, yeah, it is. So this is the original image, this is the FFT one, and then this is the one with the ADI, and you can see that it is like pretty much a perfect match, right? So our formalism is good, our formalism is working. And one question that you might ask, what would happen if I implemented like a very, very bad filter, it did not converge? And then we can try, I can put m equals 2 here, it won't be as low as m equals 10, and then we can see the effect of the ADI approximation. Might need to wait a little bit for it to run. As you can see, these filters, they take a long time to run, and you need to take care of optimizing them, which I did not do it here because I'll do it in C++. But yeah, we really need to take care of optimizing our code if we want it to run in any reasonable time. Hopefully it will finish soon. I don't know if you can hear my CPU running, but it is, I think one of the reasons that it is taking quite a while is because I am recording also with OBS, and that takes some CPU time. I did not take this into account when I recorded the video, but hopefully it should be done soon. Oh, there it is. So you see here. So here, and this is the original one. This is the exact one with the FFT, and this is the ADI, but we've poorly converged with only 2 time steps. And then you see that we have some artifacts here, especially like these furs in the hat, right? These are high frequency stuff, and we see that the ADI has some trouble. Then if you see from the Crank-Nicholson method, the frequency response for the high frequency modes, if you don't converge it enough, it's actually pretty high. So we expect for these first to have some artifacts when we don't converge, and we see like those artifacts here. Well, right, all has been very, very interesting. So we should be done for now. We know how to extend our formalism for 2 dimensions, and in the next video we will see how we add nonlinear terms to our diffusion equation, and then we'll be able to do something more interesting than just blurring the image. Until then, have a nice day and bye bye.